Hello, everybody. So the title of my presentation is multimodal per-surgical language mapping using high-gamma electrocortical, high-gamma ECoG, fMRI, TMS, and electrocortical stimulation. So as a short outline of this presentation, I'm trying to give you a quick introduction of the pre-surgical language mapping using the cortical stimulation mapping, which is a gold standard for pre-surgical language mapping, but this method has some limitation, and because of that, other non-invasive method like fMRI, TMS, or high-gamma ECoG has been proposed, and then in the next section, actually, I compare the language mapping using the cortical stimulation mapping with that using these three methods, and finally, summary and conclusion. So as a brief introduction for pre-surgical language mapping using cortical stimulation mapping, so patient with epilepsy, with intractable epilepsy, before doing the surgery, they'll undergo the subdural electrode placement for two main reasons. So one of the main reasons is the localization of the ictal onset zone using the continuous ECoG recording. So after opening the dura and putting the subdural electrode on surface of the brain, so they will monitor in our center about 1 week doing the continuous ECoG recording, and they usually have a couple of seizures. So this example shows one of the seizure event. As you can see, by looking at the ECoG EEG signal, you will see that the seizure started from some spot, and based on that, neurologists can identify the ictal onset zone here. So while we're putting the electrode to finding the ictal onset zone, another application of the subdural electrode placement would be to do the functional mapping and specifically language mapping using this technique. So to doing that, we here show that, for example, two bipolar electrodes here, these two electrodes are close to inside the Broca area, and were stimulated with a small current. And while patient is performing some language tasks, for example, reading a sentence by injecting the current, we'll see that there is a speech arrest for this patient, and we'll realize that this is a expressive language area, or some area here, if we stimulate it, we'll see that the patient have the problem in receptive language, and based on that, you can find that this is a receptive language area. Okay. So let's go to our study, which aim to compare language mapping using the cortical stimulation mapping, which, as I said, this is actually a gold standard for language mapping, and comparing this method with another three methods, high-gamma ECoG, fMRI, and TMS. In our study, we included 9 patients, which were all epileptic patients with epilepsy, and they have all native English speaker with a dominant hemisphere language on left. And we actually performed the language mapping using the cortical stimulation mapping, and also another technique, high-gamma ECoG, fMRI, and TMS on all the patients. So after co-registering the subdural electrode to MRI, and we'll find the location of the subdural electrode in pre-implementation MRI, and then normalize it to MNI atlas to have a comparison of the all patients together. And then we derive some measure to compare the language mapping of high-gamma ECoG, fMRI, and TMS with the gold standard CSM. To doing that, we assume that CSM as a reference and find the number of the true positive, true negative, false positive, and false negative electrode of each method and in each patient. And based on that, we derive the sensitivity and specificity per patient and per modality. So for fMRI, we pretty much using our clinical standard procedure for pre-surgical language mapping using the fMRI. Oops. So our paradigm was a 5-minute block design. fMRI, our task was covert object naming. Our task was covert object naming and/or a sentence completion. So this is an example of a simple sentence that we ask patient to complete this sentence for this task. And then activation detection was a p-value of 5%. We corrected for Bonferroni correction, And then we normalize the activation into the MNI coordinate for comparison of all patients together. And for the TMS language mapping, my colleague, Dr. Naranana, she actually explained the procedure. Let me quickly just give you a brief introduction of that. So we're doing the TMS language mapping using 5 hertz for 1 second, 5 pulse, and the patient performing object naming task at the baseline and during the TMS, and TMS was time lock on the stimulus onset presentation. And then for doing the procedure of the language mapping, while patient performing the object naming task, we applied the TMS in the Broca area and Wernicke area. We covered pretty much the expressive and the receptive language of the patient, and based on that, the naming performance was compared during the TMS and baseline, and the observation error, which categorized as a speech arrest, performance error, or semantic error. Each of these errors will give us one TMS site, and this TMS site was recorded in T1, in the coordinate of T1 MRI, and then this normalized to MNI coordinate, again, to compare all 9 patients. So for language mapping using high gamma ECoG, while patient performing the overt object naming task, the simple overt object naming task, we continuously record the ECoG signal. So this is an example of this object naming task. So patients see, for example, a picture of wolf for 1.5 seconds, and then they instruct to overtly name the picture that they saw before immediately after seeing a cue, which is the plus sign in the center of the screen, and so forth. So we had 100 trials of these pictures, and by collecting the ECoG data, we applied a time frequency analysis, and then using the statistical analysis, using the permutation test to find which electrode showing significant enhancement of the high gamma frequency from 50 hertz to 120 hertz, to find the electrode showing the significant language area, being identified as a language area. So this is an example patient. So this time frequency analysis showing the activity of electrode number 36 here, this electrode are within the Broca area. As you can see here, so the x-axis here is a time. So during 1.5 seconds of observation on object, you can clearly see that we have significant enhancement of the high gamma frequency compared to the baseline. And also during the articulation, when patients try to say the name of the word, again, we have enhancement of the high gamma during the articulation. Okay, so this slide actually compares the language mapping of all 4 modalities. Let's start from the cortical stimulation mapping. So this is the MNI coordinate surface map. And all electrodes of all patients are mapped here. We have about a 300 subdural electrode. So the electrode here shown in the black color are the electrode specified by CSM as a language area. And the electrode in the yellow color here, those electrodes be stimulated during the cortical stimulation mapping, but there is no effect of the expressive or receptive language for those electrodes. And the other electrode in the magenta color, those are far from the language area, and we didn't actually stimulate those ones. So in this subplot, the language mapping of high gamma ECoG is compared with the CSM. So again, I considered CSM as a gold standard and compared the language mapping of high gamma ECoG with the CSM. So as you see, the black dot here again are the true positive electrode, means that those are the electrodes identified by both of the high gamma ECoG and TMS. The red one are false negative electrode, means that these electrodes stimulate during the CSM and they have a language deficit. These are identified as a language area by the CSM. However, those are not identified as a language by high gamma ECoG. And the blue one are the false positive. These electrodes showing the significant enhancement of the high gamma during the language task, but those stimulation of those did not generate any speech arrest in those patients. And this is and the green one are the true negative, means that those are the electrodes showing no language effect in both high gamma and CSM. So again, here in this slide, you see the same thing for fMRI and for TMS. As you can see here, for fMRI, for example, we have more false negative compared to TMS, for example. And however, we have more false positive in TMS compared to fMRI. So they have different ratio of the false negative and false positive compared to each other and compared to high gamma ECoG. In this table, I summarize the sensitivity and specificity of all three methods compared to CSM, considering, again, CSM as a gold standard. So as you can see, high gamma ECoG pretty much has a very high performance, and it has a sensitivity of about 100% and very high specificity of 85%. On the other hand, fMRI has a very good specificity, about 80% across the patients, but its sensitivity is not very good. On the other hand, TMS has a moderate sensitivity and specificity across the different patients. So by looking at that, you can see that the high gamma ECoG definitely better than the fMRI and TMS. So fMRI a little bit more specific compared to TMS, and TMS is a little bit sensitive compared to fMRI. So in this slide, I compare the language mapping of all four modalities in one specific patient. So this is for high gamma ECoG, this is for fMRI, and this slide for this subplot for TMS. And this actually a language mapping of one patient who had the surgery, and after the surgery, he had a language deficit. So this is the area of the resection in this patient. And these two electrodes in black, you see in all pictures, those are two electrodes identified by CSM as a language area. As you can see, these two electrodes are far from the resection area, so there is no resected electrode that identified by CSM as a language area, and this is actually the clinical practice that the surgeon usually try to be far from the area resected by CSM. So however, we see that this, although this patient doesn't have any resected CSM electrode, but this patient has a post-surgical language deficit. And if you look at the result of the TMS, for example, you can see that the resection contains some part of the brain identified as by TMS as a language mapping, or also the resection comprises some part of the brain identified as high gamma by a language mapping. So the hypothesis that if we resect some part of the brain which identified by each method as a language area, there could be a potential of post-surgical language deficit, as we see in this specific patient. So in this, in another analysis, I use ROC analysis. And the rationale for using the ROC analysis, I see that there is no concordance between the reported sensitivity and specificity of, for example, fMRI compared to CSM in different studies. Some studies said fMRI is very sensitive, other studies said very specific, and vice versa. So I was wondering why this happened, and I see in the literature that different studies use different p-value, different significant level using different p-value, and Bonferroni corrected or not. So based on that, I realized that it might be because we increase the level of, you decrease the level of the significant threshold, it might generate different level of the sensitivity and the specificity. Actually, I have shown that using the ROC analysis, that there is a trade-off between sensitivity and specificity regarding the changing the threshold level. And also I found that the optimal value of the significant threshold at the cutoff point of fMRI and ECoG and TMS, it depends on the subject and also depends on modality. So this is the summary of the ROC analysis. I think I don't have time to go the detail of the analysis. What I'm saying that so in the ROC analysis, whenever they care for each specific patient is closer to the ideal point of 100% sensitivity and specificity, means that this method is better. So we see that high gamma ECoG here are almost all the patient close to the ideal point, fMRI in the middle, and TMS a little bit worse. So based on that, we have a measure of area under the ROC curve. That measure shows that how good is a specific method. So we see that, again, high gamma ECoG has 98% area under the curve of ROC. The fMRI is after that, and TMS is the worst comparing to these specific measure. Okay, to summary and conclusion, we, for the first time, compared language mapping using the CSM, which is a gold standard, with another 3 methods, high gamma, ECoG, fMRI, and TMS. So considering the CSM as the gold standard, we found that high gamma ECoG is the best, and fMRI is more specific, and TMS is more specific compared to fMRI and TMS, comparison of fMRI and TMS. And using the ROC, demonstrate that there is a trade-off between sensitivity and specificity of different methods. And high gamma ECoG is the best, and TMS is the worst, comparing the performance of language mapping and considering the measure of area under the ROC curve. As a future direction, so we aim to complement and replace the invasive method of language mapping using the CSM with another less invasive or more sensitive method like high gamma ECoG, fMRI, TMS, and MEG. So there is a poster presentation on Thursday for this, and thanks to all of my collaboration. Thank you.